Hello, I'm Richard Tong. Today's video is about how to solve a number theory problem such as finding the last digit of 22 raised to the 2021st power. This video is in response to Grant Sanderson's challenge, or 3B1B, his challenge of teaching math, and also some of the theories behind math problem solvings. Let's start here. So the number, this type of problem is not going to be solved by brute force. We're not going to calculate 22 raised to such a big power. That's going to consume a lot of computing power that is unnecessary because we only find out what is the last digit. So the intuitive problem solving, as taught by some of the GMAT tutors, is like this. So step one, so we look at the last digit of the base of 22 here, and we can see that really when you look at the result of this big power, only the last digit counts because all the upper digits is not going to have any impact in how the last digit is calculated. So we only have to worry about the 2 here, so we can reduce the problem from 22 to the 2021st power to 2 to the 2021st power. And step 2, let's look at how the last digit of any power of 2 behaves. Here you can see that 2 to the first power, 2 to the second power, 2 to the third power, and 2 to the fourth power. And the last digit is 2, 4, 8, and 6. And then when you go to the 2 to the fifth power, the number rotates to 2 again because 16 times 2 is 32, so it's come back to 2. So once it comes back to 2, you know that it's going to rotate in the same way as before. So let's go to 4, and then 8, and then 6. And then to 2, and 4, and 8, and 6 again. So now, let's look at how many of the cycle of 4s here are in the power itself in the 2021. And we know 2021, there are 505 4s in it, so which means that you're going to have 505 cycles, which basically does nothing to the last digit, and then comes back, and then you see here, you can convert that 2021 and simplify that to 1, and then it's basically the last digit of this problem is 2, and problem solved. So that's the kind of like the easy way to solve this problem. But what is the math thinking here? And the trick is easy because you're trying to simplify first the base and then the power cycles. But I think more fundamentally, we can translate these problems of finding the last digit of the any number into a so-called remainder problem. So remainder problem, you can also think about that as called modular arithmetic. And the last digit of the 22 to the 2021st power is nothing but the remainder of this big number and divided by 10, and whatever is remaining there is the answer you're looking for. So in the math jargon, this whole number can express that in a way of this formula. It's a big number with the mod 10, which basically that's a divider there. So the last digit of any decimal numbers, where we can use the kind of like a numbers system there and to see how this thing works, right? So any decimal number, if you look at it, it have only 10 base digits, 0, 1 to 9. And every digit position has a weight, which is a power of 10. So you can see here, like example, 234 is equal to 2 times 10 to the second power, and 3 times 10 to the first power, and 4 times 10 to the 0 power, which is 1. And then the number 2022, the original base, can be expressed as 2 times 10 to the third power plus 0 times 10 to the second power, so on and so forth. Now, take a look at how this number systems works in real world. So the original base 22, you can see the 22, if you divide it by 10, the quotient is 2 and remainder is 2. And then you express this one and saying 22 with mod 10 equal to 2. Similarly, 2022 by 4 is that you can say 2022 is a dividend, and 4 is a divisor, and 505 is a quotient, 2 is a remainder. So 2022 mod 4 equal to 2. And the formula and proof for the step 1 in the previous algorithms that you were shown there can be seen as these. So if you look at the number here, 22, which is original base, equal to 2 times 10 plus 2. So you expand that one using a so-called binomial expansion formula. And you can see there the 22 to the 2021st power can be expressed as a big series of terms that is a binomial expansion. So the formula is right there. So you use basically that binomial expansion, and then you can kind of like separate a lot of the terms. So it's actually 2022 terms that is going to be expanded by just looking at the numbers here. And there are actually n plus 1 terms. And for these n plus 1 terms, you separate them into two groups. The first one is the easy one, just the first term, which is, if you see the expression here, is the 2 to the 2021st power itself, and plus a whole bunch of terms that have 10 to some power within it. So because that's k is greater or equal to 1, so the k is the power of 10 in those cases there. So you can see that all the terms, the 2021 terms that has the 10 in it, those are multiple of 10s, right? So the remainder of those doesn't really matter because it's going to end with a 0. And you can eliminate that from the remainder part of it. And the only thing, so you only need to worry about the remainder of the first term, which is 2 to the 2021st power. Now we look at the part that is the cycle part of the power. And you can see here, we already reduced that big number 22 to the 2021st power to a still very big number, but a much smaller 2 to the 2021st power. And this part we can see is a 2 to some, to nth power, and see how this power behaves. We can also look at not only 2, but also the other 9 digits that we have in the decimal systems. Here is the chart that you can see here. The top part of it is the calculation of all this to the ninth power. And the bottom part of it is just the last digit. It's the kind of like the remainder with mod 10. So you can see here that like 0 is always 0, 1 is always 1, 2 is 2486, 2486, 2486, 3 is a 3971, 3971, 4 is a 46, 46, 46, 46. 5 is always 5, 6 is 6, 6, 6, 6, all the way 6. 7 is 7931, 7931, 7931. 8 is 8426, 8426, 8426. And 9 is a 919191. All that. So the basic, if you look at this bottom chart here, the part from 1 to 4 and the part from 5, 6, 7, 8. So these two parts, they are exactly the same. So basically we're repeating. So that's why we have this cycle of 4 that is not only repeating for the power of 2, but power of all of the 9 digits that we're seeing here. Because again, 0, 0, you can still see them as like a 0 in a block of 4 repeating. So altogether, this whole block, any of the 10 digits, is going to repeat by itself every 4 cycles. So let's look at the formula for step 2. And here is to find out the cycles. So what we already see is that, well, this is kind of like a general form of the solving this type of GMAT problems, finding the last digit of any power. And then first, you find out what's the last digit, D, in this case, from a number from 0 to 9. And then you find the how many, what is remainder if the power is doing a mod 4 operation. So basically, like the 2021, you eliminate all the power of 4, all the multiples of 4s, and then you basically are left with 1, 2, 3, 4. In the case that it's a divisible by 4, let's use 4 for the sake of it, because the to the 0 power is 1. And in some cases, like when the last digit is an even number, that it's going to return to 1. It's going to return to 6 rather than return to 1. But all the odd numbers are going to return to 1. All the other numbers, all the like 2 is going to return to 6, and so on and so forth. So once you find the 0, the 1, 2, 3, and 4's power of the any digit, you can basically replace that with your answer there, right? So in this case, we can say any number of integer a to the nth power, you use a reduced base and a reduced power. So the reduced base is from 0 to 9. The reduced power is from 1 to 4, 1, 2, 3, 4. And then you can basically use that to get your answers. Now let's do a couple examples of this method that we have proved. First, let's take on a bigger number, 2022 to the 2021st power, and the remainder modular 10 is, first of all, we simplify the base, use the last digit, which is 2, So the problem becomes, what is the remainder of 2 to the 2021st power? Just like we did with the previous example, let's do a 2021 with a modular 4, and the remainder of that is 1, which means that after 505 cycles, we're getting back to 2 to the first power, which is 2 again. Problem solved. The second one is a little bit trickier. Here is the 7 to the 400th power. So first of all, it's actually easier because we don't have to deal with the base. The base is the 7, which is the single digit. But look at the power of 400, so which means that we're going to do full 400 cycles. If you look at the chart, the full cycle, which means that we basically have to go from 1, 2, 3, 4. So we'd go to the 4th. And in that case, this is going to be, if you check here, the 4th remainder is 1, which basically 7, 49, 9 times 7 is 3, and 3 times 7 back to 1. So we're going to go to 1 here. So that's the problems that we have solved. Now let's go above and beyond what we have been talking about. Where does this magic cycle of 4 come from? Why all the digits, when we do the modular 10, have these magical cycles in the modular 10 remainder always come full circle after the 4th iteration of the power operation? And so here we're going to touch upon some of the number theory topics, especially modular arithmetic. And also we're going to touch on a little bit of the group theory. Actually, for example, we're going to see some of the properties of a commutative ring, for example, in the channel remainder theorem. We're actually not going into the part there, but this is going to give you a hint of why some of these properties are exhibited in the remainder problems. And actually, we're going to also talk about some more difficult problems with modular instead of modular of 10. Let's try it as a modular with other numbers. So here is kind of like a quick introduction of the modular arithmetic. So think about after the operation of an integer and the remainder part of it, we call that the set Zn, and Zn will be in this case, the residual numbers that coming from a modulo operation. And that operation, the modulo operation of when the mod is 10, you're getting the 10 digits 0 to 9. But for any number, there could be that residual numbers. So if you have a modular, say 3, then you will have 0, 1, 3. There will be the numbers. The interesting thing about these modular numbers themselves, they actually form a pretty nice finite group. If you look at the group theories, they're actually in a finite modular group there. And for these operations on these groups, you can see the element of the groups. And if the element, if you do A plus B, you have this commutative properties on both the addition operation, but also on the multiplication operation. So you will know that actually this will be a commutative ring. Again, well, it will also have other properties, but this is very important properties that give us some really good advantage when we're manipulating them and looking at some of the symmetries and also the operations on them. You also have associative properties on both the addition operation and also the multiplication operation. You certainly have both the multiplicative identity and the additive identity, which is 0 and 1 here. And there is some additive inverse, which the plus and minus in this case are existing here. And also there's the multiplication associative properties, which means that A times B times C equal to A times B times C here. And also you have a multiplicative distributive property over addition, which means that A times B plus C equal to A times B plus A times C. So this actually, if you look at this, these are very similar to integer, right? So it's actually, they share a lot of the good properties with integer. The only thing though is that it's finite, but a lot of the properties is very helpful when you are manipulating them in this ring or in a field. So there are several theories that are at work here when we're trying to getting a more generic formula to solve any integer to any integer power and find the remainder problem. So one thing that is called the Fermat's-Little theorem. So, and this is actually a very interesting one. So what it's saying is that if P, which is the module, is the modulo P, and there is this nice property. Basically, what it's saying is that the A to the P minus 1 power always is congruent with 1, which is very, very interesting here. That again, the P has to be a prime number, right? So there's definitely that little bit of the restriction here, but this is actually giving us some really important thing that we're going to see. It's going to help us to simplify things so much easier. There's a lot of proof for these theorems. Actually, there is a specific wiki page that devoted to all the proofs that the Fermat's-Little theorem can be proved. I'm not going to the proof themselves, and for the audience who are interested in that, look up the Wikipedia page on Fermat's-Little theorems proofs, and then you're going to see a very interesting type of proofs. Some of them are using similarly the one that I used earlier, using the binomial expansion, or I mean, you can also use combinatorial type of mechanisms to prove it, which are very nice. And there's the more general form of this theorem, which is called Euler's theorem. And there's actually a number. This is also called the Tolchin number, or the Euler's phi function. That's, again, there's a lot of phi functions, but this function is the Euler's phi function that's specifically used in the modular arithmetic here. And what it's saying here, again, is very similar. You can see these two have very similar form here, but this one is more generic, which means that the n, which is the mod, can be any number. It doesn't have to be a prime number. So what it's saying is that if the n is greater than 1, and then a and n are co-prime, which means that the modular, the mod and A, which is the base here, if there are co-prime, then A to the power of this quotient number of n is actually congruent to 1, which means that the A to the Totient number power minus 1 is going to be divide n. So that's a very, very I would say powerful way of solving all the problems, right? Because again, if you look at it, one of the extension for this theorem is this corollary that we actually use, that we can solve any modular operation on a power function. So because this corollary, which directly derived from the Euler's theorem, is that A to the x is congruent to A to the y if x and y having the same remainder when divided by n. Means that, again, so that's so here the quotient, the Totient number of 10, which we saw earlier to solve the digital, the last digit number, last digit problem there, is that the Totient of 4 is that magic number, so that it's any of the powers when they are, every 4 turn or every 4 iterations, they're going to rotate back in terms of the mod, the remainder. So that's give you that magic number. But what is the Totient number, right? So the Totient number is actually very interesting. It's basically the number of co-prime numbers below n. So for example, if any prime number, right? If you look at the prime number, so because prime number means that other than 1 in and itself, it will not have any number that that has a common factor with it. So which means that it's any number below the prime number, it's going to be prime, co-prime with it. So which means that the Totient number for any prime number is just the prime number minus 1, right? So that's why we're saying Fermat's-Little theorem is a unique or a subset of or is a special condition when the n equal to p here, when it's a prime number. But say if you have a non-prime number, say for example the number 10 here, the number 10, if you look at the numbers below 10 that are co-prime with it, including, so 9 is 1, 8 is not co-prime because they have the common factor of 2, so only 9, and 7 is, because 7 is a prime number, so definitely is co-prime with 10, and 6 is not, because all the even numbers have a common factor of 2 with it, so that basically we're looking at 9, 7, 5 is not, because 5 is a divider of 10, and then 4 is not, 3 is, 2 is not, so you only have 9, 7, 3, and 1, right? So those are the 4 numbers that are below 10. that are co-primes with it. So in this case, that that number is 4, right? So that's the total number is 4. But you can also calculate this number with a neat formula, which basically is saying the total number of 10, you can factor 10 into primes, in this case, co-primes numbers 5 and 2, and they can be, you can just multiply these two. So the co-prime, the total number or the number of 5 is 4, and the total number of 2 is 1. Both are prime numbers, so it's prime number minus 1. So you get 4 times 1 equal to 4. So basing on this theory, we can know that a to the x, a to any number of the power, when you apply the modular n function, in this case modular 10, and then it's going to be congruent with any cycle 4 equivalent of that, right? So basically that we can say that if x and y are they share the same remainder when divided by 10, then they will have the same remainder with the power with any integers to those two powers. So that's the kind of like the long way to looking at it, right? So you can see here in the mod of 10 problems, you can see that theory just applies, and then the magic number 4, this is where it's coming from. At least this is one of the ways to prove that it's this cycle 4 applies to all integers that has a modular, that has when it's apply a modular arithmetic against 10. So that's a very, very powerful thing, which means that in the future, if you look at any time when they're looking for the last digit number, so you know for sure that the cycle 4 applies. And now we can use that to solve some more interesting questions that we just talked about earlier. Since this Fermat's Lido theorem and also the Euler's theorem both can be used to help with calculation of remainders, and the remainder of any base and with any mod, we can use this approach, right? So basically, you apply, again, 3 steps. The first step is looking at the base itself and see whether the base have, you can get to the level of within the smallest possible way, right? So in this case, when you look at 5 with mod 7, okay, 5, you don't have to do anything because it's already below 7. But when you look at 5 to the 200th power and the modular is 6, is very helpful here because this 6 is arithmetic number of 7 minus 1, right? Because we're talking about the power applying a modular of 7, and we know that any power in this case at the power position, you need just looking at the congruent number that is a remainder of 200 by 6, right? Because that 6 is that magic number there. And you can see here, so 7 with mod 6, 200 with mod 6, the remainder is 2. And the calculation now becomes so simple. So all you need to find is find 5 to the to the second power, which is 25, and 25 apply modular 7, and that's 4, right? So you got the remainder of 5 to the 200th power mod 7 and equal to 4. Now looking at a problem that the mod itself is not prime number, so you cannot use the easy way to calculate the phi, but still it's not that difficult, right? Because again, if you look at the 9 here, so what is the magic number? Let's do a counting here. So below 9 you have 8 is 1, 7 definitely, not 6 because I have a common factor of 3, and then you have 5 is 1, 4 is 1, 3 is not, and 2, and then 1. So the coprime number there is 6, right? So we know the magic number is 6, and apply the same thing, 200 mod 6. We just calculated from the previous question, so we know the remainder is 2. So 7 to the 200th power modular 9 will be congruent to 7 to the second power, which is 49. And 49 mod 9 is also 4. So you solve that problem. And now let's look at a bigger modular number. So we're basically saying, what's the last 2 digit of 7 to the 201st power? In this case, okay, the last 2 digits is really mod 100, and then you can calculate the phi number here. So that's the kind of like the formula. It's also Euler's algorithm or formula there. It's actually, you can use the number n times 1 minus p1. Basically you do a prime factorization of 100, which basically you got 2 to the 2 times 2 times 5 times 5. So basically the formula is n, which is in this case 100, times 1 minus 1/2, which is the first prime number there, and then 1 minus 1/5, which is the second prime number there, and then you calculate this all together, and you got 40, which is the magic number of mod 100. Mod 100 is actually 40, so which means that the cycle comes in the cycle of 40. So you look at the power there, the power is 201, and then 201, when you apply mod 40, is equal to 1, so which means that we can simplify 7 to the 201st power, and it's congruent to 7 to the first power, modular 100. So very interestingly, you can say is that the last two digit of 7 to the 201st is actually 0 and 7. That's a very powerful computation out there. So again, it's also very interesting. So the summary here is that we look at this problem of finding the last digit of any power of a integer, and basically the math behind this is, we're looking at number theories, we're looking at modular arithmetic, and so you not only learn how to do the trick, but also you learn some of the foundational theories behind it, and then you can expand that by looking into more of the group theory stuff and all these other type of things. But also we want to illustrate is that how do we really analyze and solve such number problems, right? So there's the toolkit from the modular arithmetic. There's a toolkit from group theories, especially rings that you can use to your advantage. But I think also I want to allude to some of the practical use for this modular arithmetic. It's not only to score a high score in the GMAT, but actually you can also use them for a lot of practical uses. So modular arithmetic is one of the foundation for number theories, and it's also used again very extensively in the group theories. So a lot of group theories themselves, the theorems are solved by the finite modular groups and so on. And then ring theories, knot theories, and abstract algebra. But when you apply that in the field, it's used extensively in computer algebra. Like for example, how do you create the chips that try to do arithmetic operations? There's a lot of this modular stuff that are applied to binary numbers, and also cryptography, like for example, the RSA theorems is built on top of these. And computer science, a lot of the foundation of computer science is basing on this discrete modular arithmetic. And also chemistry, as well as visual and musical arts. So it's not just to solve this trivial GMAT or math computation questions, but they actually have a really powerful use. So thank you everyone, and enjoy the video, and hopefully you can learn beyond the problem solving algorithms, but really looking into the kind of like the things behind it. Thank you.